Today we start discussing module 3 algebraic number theory. In this video we review the topics from the course abstract algebra that help us to understand algebraic number theory. One of the fundamental tools that we use to study algebraic number theory is fields. The important structures are rings and fields. A ring is the fundamental structure of the ring theory. If multiplication is commutative in a ring, we call it as a commutative ring, and if it possesses multiplicative identity, we call it as ring with unity. With these two properties, we call a ring a commutative ring with unity. From commutative ring with unity, we can think of two important structures: integral domain and skew field. The first structure is the consequence of the study of multiplicative inverse in the ring. In fact, the commutativity is not needed for this structure. The later is the consequence of the study of the divisibility. From these two structures, we can reach field. Now I left an exercise here. Find the examples and counterexamples of these structures in the ring theory. Now we should remember some important ideas of ring theory. First, we have characteristic of a ring R. It is the least positive integer n such that n times a equal to 0 for all a belongs to R if it exists. Otherwise, the characteristic is defined as 0. Then we have units of the rings. The elements which possess multiplicative inverse are called units of a ring. So this is an important study. We will begin our syllabus with this. Another important idea is factorization of elements. We know that polynomials play an important role in algebraic number theory. The polynomial rings are important examples as well. So you must review the polynomial factorization, and as a consequence we can discuss irreducible polynomials. And if we study field extensions, we can see an important theorem regarding this field extension. The most important theorem in this section is Kroneker's theorem. This is the bridge from ring theory to Galois theory. In fact, we are using these ideas in algebraic number theory. Then you need to remember algebraic and transcendental numbers, then minimal polynomials, etc. We have different types of extensions, field extensions, say finite extension, simple extension, algebraic extension, etc. So we will discuss this finite extension in our syllabus. So that is an important tool in our algebraic number theory study. So if you discuss finite extensions, we can think of degree of an extension field and degree of an irreducible polynomial over a field. All this. After all, you need to discuss some important idea of algebraic number theory. You might not discuss this in your degree classes and PG classes. That is about symmetric polynomials. You need to go through chapter 1 of our prescribed textbook for module 3 and 4. In chapter 1 contains the some discussion about symmetric polynomials. And in the chapter also contains the idea of modules. Modules is a vector space over a ring rather than field. So we are considering all the axioms of a vector space over a ring instead of considering fields. So you must go through all these topics in chapter 1. Then you have you have to familiar with some terminology in your textbook. If we consider a group G, let it be an abelian group, then we shall use additive notation for G. That is, the group operation will be denoted by plus symbol, and the identity element of the group is denoted by 0, and the inverse of an element G is denoted by minus G. Okay. This is the terminology used in this textbook. For the powers of an element G, we will use the notation for G square, we will use 2G. For GQ, we have 3G, etc. These are the important terminology in the textbook throughout our module 3 and 4. Actually, we need to review chapter 1, 2, 3 of our prescribed textbook. So here I write some definitions, the important definitions that we have to use in your chapter 4, 5, etc. So this is the definition of finitely generated abelian group. If G is a finitely generated Z module, so that there exists G1, G2, etc. Gn belongs to G such that any G belongs to G, capital G, can be written as G is equal to some m1 times G1, m2 times G2, etc. mn times Gn for some mi belongs to Z. Then G is called finitely generated abelian group. So if we define G is in this manner, you can think of linear independence with respect to this this expression. Basis elements of this finitely generated abelian group, and some important theorems, theorem 1.16 and 1.17 in chapter 1. Okay, so these are the things you need to go through the chapter 1. In the second chapter, you need to review some properties of algebraic numbers, number fields. Probably this will be a new definition for you. Number fields. Actually, number fields is a extension field with some property, and then conjugate elements, then discriminant and properties of discriminants. Then you can think of algebraic integers. Algebraic numbers are the complex numbers with minimal polynomial in rational numbers. Then for algebraic integers, we need to go through the definition of algebraic integers and its properties in that is in the chapter 2, and integral basis, definition of integral basis and properties. There are a number of theorems in chapter 2. You need to go through all the statements of those theorems. Then the chapter 2 contains the idea of norms and traces. Then ring of integers. Ring of integers means ring of algebraic integers. From chapter 3, you need to read about quadratic fields and its properties. So you need to read about the statements of all the theorems in chapter 2 and understand those theorems. We need to use these theorems as a reference in chapter 4 and 5, and some important theorems of chapter 1 and chapter 3. I have already mentioned the important theorems in chapter 1 as 1.16 and 1.17, and you read all the theorems, important theorems in chapter 3 that you have to use as references.